So acids, alkalis, and titrations. We start with the pH scale and talk about the indicators first. The pH scale ranges from 0 to about 14, and it tells you how acidic or how alkaline the solution is. We use the pH scale in simple numbers to make it easier for us, and these numbers actually represent specific part of the acidity or alkalinity. Like as you can see from here that 0 to 3 are representing the strongly acidic solutions. 4 to 6 are representing the weakly acidic ones. Then 7 exactly is neutral. 8 to 10 are weakly alkaline. And lastly, 11 to 14 are the ones which we call strongly alkaline. Which means if 7 is exactly neutral, then moving lower than 7 would be increasingly acidic, and moving higher than 7 all the way to 14 becomes strongly alkaline or increasingly alkaline. That's how we divide them. The examples are also written over here clearly that hydrochloric acid is the strongly acidic one. Vinegar is a good example of weakly acidic. We also call it ethanoic acid. Water, pure water, or sodium chloride solutions are the example of neutral ones. Ammonia solution is the example of weakly alkaline solution. And finally, sodium hydroxide solution is the example of strongly alkaline one, right? So this is an easier way to go through the pH table. They have written the same examples over here. Moving on, how do we measure pH? Now, we actually use indicators to measure pH. Indicator is any substance that has different colors depending on the pH that can use or that is being used in a solution, in any kind of solution. So what we do is that we usually commonly use universal indicator. A universal indicator is actually a mixture of indicators. It changes its color in a gradual way over a range of pH value. It can be used as a solution or as a paper. The most common form is known as full range indicator, or this one, universal indicator. It's common because it imitates the rainbow. If you remember, the rainbow has actually 7 colors, and we usually talk about those colors from red all the way to violet. So this universal indicator can imitate those colors, red being the side of acidic, while violet being the side of alkaline. So it can imitate the exact rainbow colors. Red means highly acidic, orange means weakly acidic, or yellow means very weakly acidic. Green is going to be neutral in this case, and blue, indigo, and violet represent from weakly alkaline to strongly alkaline, respectively. The same thing is written over here, right? But it isn't a very accurate because we need to match colors with the one that is given us on the papers or the chart with the one that is we can see from the solution. As you can see over here, the one that is acidic is slightly reddish in color. The one that is less acidic is yellowish in color. This one is less acidic, right? And the one that we can find blue is actually alkaline in its color. All right. So there are various systems that we can discuss by seeing just the color. But remember, you can measure pH much more accurately if you're going to use a pH meter. A pH meter can easily tell us the pH up to 1 or 2 decimal points, and that's the most accurate way of measuring pH. So whenever you are talking about measuring pH in paper, you're always going to prefer a pH meter because that's going to be the most accurate one. Your second preference, if you can't use the pH meter, should be the universal indicator paper or solution, because both of them are considered as the most accurate one after pH meter. Right? All other indicators are very limited. not as good as universal indicator. We can discuss a few of them in the upcoming topic. So moving on to acid-alkali indicators, as I just said, indicator is a substance which changes its color according to the pH of the solution. So there are different indicators that we can discuss. For example, litmus shows red color in acid and blue color in alkali. Methyl orange shows red in acid, while it shows yellow in alkali. Phenolphthalein, or you can also pronounce it as phenolphthalein, can show colorless in acidic and pink in alkali. Universal indicator, however, is the best. It shows red in acidic and blue in alkali. However, this blue can be as dark as violet or indigo. Now, here, litmus, they're talking about litmus. Litmus is red in acidic solutions and blue in alkaline solutions. But it's important that we need to understand their neutral systems. In neutral solutions, the color of litmus is purple, which is actually an equal mixture of red and blue. Universal indicator is green in neutral solutions. So everyone has also their neutrality, which is probably not written over here in the book. So if we discuss neutral, litmus is purple. Methyl orange is actually orange. That is not probably written over here. Phenolphthalein is colorless in neutral systems, while universal indicator is green in neutral systems. All right. Litmus can also be used as a solution or litmus paper. Litmus paper only comes in two colors, red and blue. Blue can be turned to red in acidic systems, and red can be turned to blue in alkaline systems. That goes for litmus paper. All these are actually solutions. So remember, these are all solutions. Any questions so far?
How can you tell if a solution is neutral from litmus paper?
The only advantage of litmus paper is that we can never tell when the solution is neutral, because then there would be no change. As I'm talking about two colors for litmus, the red stays as red in neutral system, the blue stays as blue in neutral system. So as nothing happens to them, we can't tell whether the solution is neutral or not. That's the advantage of the disadvantage of litmus paper. That's why we started using universal indicator paper. At least it would show green in neutral systems. All right.
Okay.
Well, let's move on. So let's discuss acids. An acid contains hydrogen, and when acids react, the hydrogen is replaced by something else. All acids have replaceable hydrogen atoms in their structure. For example, when hydrochloric acid reacts, it has hydrogen, this one, and when it reacts with sodium hydroxide, this specific hydrogen is replaced by a metal, in this case sodium. As you can see in this formula, that they have hydrogen that can be replaced. HCl, this H is replaceable. HNO3 or nitric acid, this H is replaceable. Sulfuric acid actually has two replaceable hydrogens. Acetic acid has four hydrogens, but only one of them is replaceable. This one is not replaceable, being the part of organic structure or a link to carbon. Phosphoric acid has three replaceable hydrogen atoms. So in different acids, there are different numbers of replaceable hydrogen atoms, because of which we call them acids, and they can be replaced by anything else when they react as an acid. For example, in this specific reaction, it is being replaced by the metal sodium. Now, not all of the hydrogen acids are replaceable, just like the one that I've told you about in ethanoic acid. For example, in ethanoic acid, only the hydrogen attached to oxygen is replaceable, not the ones that are connected to carbon. The reactions of carboxylic acid, such as ethanoic acid, are discussed further in chapter 27, where we'll discuss the organic chemistry. Right? So the acids, when they are dissolved in water, they actually dissociate, they break down. We also use the word ionize for them to form hydrogen ions. For example, HCl, as soon as we dissolve it in water, it breaks down into positive ions and negative ions, and the positive ions are bound to be hydrogen ions. That happens with most of the acids. Take a look at nitric acid. When it breaks it down in water, it forms the hydrogen positive ions and it forms the nitrogen ion. The same happens to sulfuric acid. It also forms the positive hydrogen ions and the negative sulfate ions. So most of the acids, whenever dissolved in water, they dissociate or they break down, giving the positive hydrogen ions and a negative ion, and an anion, of course. So when we are measuring pH, we are actually measuring the concentration of these H positive ions or hydrogen ions in the solution. This is why the H in pH is written with a capital letter, because that's the concentration of hydrogen ions. We can define acids as substances that act as a source of hydrogen ions whenever they are dissolved in water or in solution form. At next levels, we will discover that pH is defined by a mathematical equation in which we use logs or logarithms to explain the concentration of hydrogen ions as pH. But that's a part of A levels. Let's skip it for now. Bases. Bases are substances that neutralize acids by combining with the hydrogen ions in them. When we are referring to a base at this level, we usually mean a metal oxide, maybe a metal hydroxide, or ammonia. All three of these categories actually can be considered as a base. For example, a metal oxide, calcium oxide, can be considered as a base, or calcium hydroxide, like this, can also be considered as a base or ammonia. You may change the metal, its oxide and hydroxide will definitely act as a base. You may replace calcium with sodium. This would give you sodium oxide and sodium hydroxide, or magnesium oxide and hydroxide, potassium oxide and hydroxide. They're all bases. So it's easy to give examples of bases. Let's talk about alkalis because we have been using the word of alkalis rather than bases. Some of the bases dissolve in water. They're actually soluble and they form solutions that contains hydroxide ions. That's why we call them alkalis. So actually alkalis are a branch of bases. It's just that they're soluble in water. Now alkalis are a very good source of hydroxide ions in solution, just like the acids were the source of hydrogen ions in solutions. Examples of alkalis are sodium hydroxide and potassium hydroxide, just like I was telling you about examples of bases in the previous topic. All of the group 1 hydroxides are actually good examples of alkalis. They're easily soluble in water and they break apart or dissociate to give a positive ion, but negative ion is bound to be the hydroxide ions. For example, this one. Or in case if you change your examples with potassium hydroxide, of course, that is also going to give you a positive ion, but the negative ion would be the hydroxide ion. You can easily put the state symbols of aqueous against all of these because they only are converted into ions when they are dissolved into water. The other alkali you will meet is a solution of ammonia. Ammonia reacts with water to form ammonium ions and hydroxide ions, and that's how the reaction goes. So ammonia is actually a gas which can be dissolved into water, and it then is known as ammonia solution. It gives ammonium ions and hydroxide ions. It's a proper chemical reaction. Once again, as it becomes a source of hydroxide ions, we also call it an alkali. All the alkalis have a pH greater than 7, as we discussed in the start of this chapter. Moving on, other alkaline solutions, there may be other substances which may be soluble metal carbonates that react with water just like ammonia did, and they form hydroxide ion. One of those examples is sodium carbonate. Sodium carbonate can be dissolved into water. It actually reacts with water, produces sodium hydroxide and sodium bicarbonate. Sodium hydroxide is then actually an alkali, which gives OH negative or hydroxide ions. So we simply call sodium carbonate as also given a source of alkaline solutions. Apart from this fact, ammonia solution is sometimes called ammonium hydroxide. Now, it is an alkali. It's actually used in some cleaning products. Some universal indicator solution has been added to the beaker to tell you that the color turns to blue, proving it's an alkali. Cleaning products, such as kitchen cleaning products, the counter cleaning products, or oven cleaners, usually commonly contain ammonia solution. Now, the ionic equation for the carbonate that we were talking about previously on the previous page, take a look at this page, just a second. If we go one page back, you would see sodium carbonate plus water gives us sodium hydroxide plus sodium hydrogen carbonate. You'd find the same equation over here. It's just that we have taken out the sodium ions, forming an ionic equation. The carbonate ions reacting with water gives us hydroxide ions and hydrogen carbonate ions. That's why we call sodium carbonate a source of these hydroxide ions, and we call it alkaline solutions. There are not many soluble carbonates, but sodium and potassium carbonate are both alkalis with a pH greater than 7. This is due to OH negative ions in the solution. Only some of the carbonate ions react with water, so these solutions are very deeply alkaline. Examples are sodium and potassium carbonate. Are we clear? Shall we move on to reacting acids with bases and alkali?
Yeah.
Okay. So acid react with bases and alkalis. We call this reaction neutralization reaction because acids are actually neutralized by alkalis or bases, or alkalis on the other hand are neutralized by acids. They actually neutralize one another. How do they do that? Let's discuss it with the help of examples. For example, acids with bases. Metal oxides such as copper oxide and magnesium oxide are bases. I have previously quoted the example of magnesium oxide. Copper 2 oxide reacts with hot dilute sulfuric acid. This is a neutralization reaction because it's going to produce copper 2 sulfate solution and water solution. The basic part of neutralization is that it forms a neutral solution such as water. Remember, when we were discussing pH, we said that pure water is neutral. So this reaction is known as neutralization as it produces a neutral product. Copper 2 oxide is an ionic compound. It contains oxide ions. What has happened to this reaction is that the hydrogen ions from the acid have combined with the oxide ions from the base, and they form the neutral component water. Hence the word neutralization reaction. If we move on to the second type, in which acid reacts with alkalis, this is also going to be simple and pretty straightforward, and it's going to be same to the previous reaction in the terms that it's also going to produce water. So the alkali would be a source of hydroxide ions, the acid being the source of hydrogen ions, and they're going to react together to form a salt and water. Water being the neutral product gives us the name as neutralization reaction. Sodium hydroxide and sodium chloride are both ionic compounds. So they can be presented as ions. You can simply convert them into ions. For example, this can be written as chloride ions and sodium ions. On the other end, the sodium hydroxide ions can be written as sodium ions and hydroxide ions. My bad. This one actually comes as a part of these chloride ions. These ones. Now this acid can be written as hydrogen ions and chloride ions. Now this far up are the reactants written as separate ions. They form a salt which can also be dissociated into water, and water is the only one that is liquid over here, so it hasn't been broken down into ions. As this is aqueous, so we can write it in two separate ions, this one and this one. This one's also aqueous. We can write it as two separate ions, hydrogen ions and chloride ions. This one's also aqueous. We can write it as sodium ions and chloride ions. But as this one's liquid, we don't break it down into its ions. So an easy way, another way to write ionic equations is to convert anything that is aqueous into its respective ions. But anything liquid, solid, or gas will not be broken down into its ions like this. What we do is that we cut the ones, or we cancel out the ones that are same on both sides. For example, if this is the center, at this side we have sodium ions, we can cut them with the sodium ions on this side. The chloride ions from this side can be cut out with the chloride ions from this side. We are left with hydroxide ions written over here, hydrogen ions written over here, and simply water written over here. That's the ionic equation to any neutralization reaction, because acids and alkalis actually are the sources of hydrogen ions and hydrogen ions respectively, which react together to form neutral water, hence the name neutralization reaction. So most of the neutralization reactions will end up having the same ionic equation. This is the easiest kind of tip to write the ionic equation for neutralization reactions. You get the point? Can you hear me?
Yes, can you repeat the question?
Now, the point I'm trying to make, I was just asking you about getting the point. The only point I'm trying to make is that all the acids are actually suppliers of H positive ion. And I'm saying that all the alkalis are actually suppliers of hydroxide or OH negative ions. So whenever these two react, they're bound to form the water, right? Water, which is actually neutral component here. So that's why it's written in the ionic equation form like this. Because the negative ion in the acid and the positive ion in the alkali, they actually react together to form the salt, this one, and actually we call them spectator ions. These are then known as spectator ions. Spectator ions are the ions which do not exactly participate in this neutralization reaction, because hydrogen ions from the acid tend to rush towards the hydroxide ion in the alkali to form water. What we are left with is the positive ion of the alkali, sodium ions in this case, negative ions of the acid, chloride ions in this case, to form salt. As they are left out, so they react together and form salt, we call them spectator ions. Right? That's how we come up with this ionic equation. And the point I was trying to make is that every neutralization reaction of an acid or an alkali on the planet will always give us the same ionic equation, because every acid will contain H positive ions, every alkali would contain OH negative ions, and whenever they would react, they would only form water. So it's pretty easy to write an ionic equation for a neutralization reaction because it stays the same every single time. Right?
Okay. Yeah.
This works as a great tip of writing ionic equations for neutralization reaction. Moving on, titration. Titration is actually analytical chemistry procedure to follow the course of neutralization reaction between an acid and an alkali, and titration can be used to find out that how much of the acid or the alkali reacted with a certain volume of the other. So if we know the volume of acid, we can find out the volume of alkali that reacted, or vice versa. The same thing goes with concentration. Let's go through the technique to understand this point. Our first step is to measure out a specific amount of an acid using the pipette and the pipette filter. As pipette and pipette filter, let me explain, are the most accurate piece of equipment. So measuring out the accurate 25 cubic centimeter out of it, and not even a drop more or less, can easily be done with the help of a pipette. We then take this pipette and transfer all of the acid to a conical flask. On the other hand, we're going to take a burette. Burette is the second most, actually burette is almost equal to pipette in terms of its accuracy, and Both burette and pipette are the most accurate pieces of equipment in the lab you're going to use for titration. So what we're going to do is that we're going to take a burette, we're going to clamp it to a stand, and we're going to fill up the burette with the alkali solution. We take the initial reading of the burette and we record it up to 2 decimal places. Burettes, as they are pretty accurate, can give you the reading up to 1 or 2 decimal places. So up next, we add a few drops of our indicator into the flask. We then start running the burette, the alkali, drop by drop into this flask. So we're going to use this system drop by drop a little slower with patience until this one changes its color according to the indicator. As soon as that happens, we note the final reading. We have already noted the initial reading on the burette. Let's suppose this was the initial reading. We note down the final reading on the burette. Let's suppose this is the final reading. And then we try to work out this difference. This difference can easily tell us that how much the amount of alkali has been used. All right. So we started off by saying that titration can easily calculate the amount of acid we have used against an alkali or vice versa. So we did the same thing over here. Now, calculations involving titrations are discussed in chapter 6. This before and after diagram of reading a burette tells us that the burette started off with, take a look at this, 2.1 cubic centimeter, and we used it all the way to 23.85 cubic centimeter, right? So we can always work with this. Can you understand how I took it to be 23.85 for this one to be 2.1?
Yeah,
good.
That's on the line. Yeah.
Good, good. So the alkali is added to the acid from the burette and the indicator changes color. Usually do a rough titration first in order to find out approximately how much alkali is required to neutralize the acid. Imagine we found out that we require roughly 22.50 cubic centimeter of alkali in the rough titration. We would then do an experiment again, but this time running in about 20 cubic centimeter of alkali quite quickly, swirling the conical flask all the time to mix the solutions. We would then add the alkali pretty slowly, drop-wise, until 1 drop of alkali causes the indicator to change from its acid color to the alkaline color. We then know the amount of needed for neutralization to within 1 drop. This is about as precise as we can be. So in the above titration, we could also have added the acid to the alkali, but it's easier to see the indicator turning pink rather than going colorless, as we were talking about phenolphthalein. So it's a little bit at disadvantage to take it to colorless rather than to turn it to green, pink, my bad. So we try turning it pink. But if you're using a different indicator, you can switch the places of acid and alkalis. You can take the acid in the burette and the alkali in the flask for another experiment. That's completely all right. So it totally depends upon you to which one you're going to know and which one you're going to find out. So the one that you already know, you're supposed to put that in the flask, and the one that you want to know about, put that one in the burette. So if you want to know about the acid or how much amount of acid can neutralize an alkali, put the acid in the burette and the alkali in the flask. So when reading a burette, it is important to remember that the numbers increase from top to bottom. 0 is at the top and 50 is at the bottom. We normally record readings from the burette to the nearest 0.05 centimeter. Therefore, all readings should be written down 2 decimal places. The second decimal place is given as 0 if the level of the solution is on line, and 5 if it's in between the lines. The readings from the burette in figure 16.8, this one, should be recorded as shown in 16.4. So let's move on. Let's take a look at table 16.4. So that's 2.10 and 23.85. The rough titration told us about 22.5, but the exact accurate titration gave us the idea of 21.75, which is pretty accurate. The volume of alkali added is this one. Various indicators can be used. Methyl orange can be used, but not universal indicator. We do not use universal indicator because it has a range of colors and changes gradually between them. This means we will not be able to see a clear endpoint for the titration. So we do not use universal indicator for titrations. We actually use universal indicators to check for different solutions that whether how are they going to work and give the color, and we can then note down the pH. A key point, the endpoint of the titration is the point at which the indicator changes color. The point at which indicator changes color does not necessarily indicate the point at which the solution is neutral. The pH changes very rapidly near the endpoint of the titration, and in some titrations, one drop of an alkali can change the pH from about 3 to 11. So the most precise we can be is to know neutralization point to within one drop. That's the best we can do. There are other solutions to getting to the endpoint of the neutralization point, but we discuss titration up to this far at this level. And that's about it for this chapter.